Welcome back students for the fourth video lecturing on the electrical conductivity of metals. In this video I am going to discuss about expression for electrical conductivity of metals in the case of quantum free electron theory. Upon that we shall discuss about the success of quantum free electron theory. So in order to understand the expression for electrical conductivity of metals given by the Sommerfeld, we need to know about the few basic definitions such as Fermi temperature, Fermi velocity, and mean free path and mean collision time. I have already discussed mean free path and mean collision time. So next is I will going to explain what is Fermi temperature. The Fermi temperature is the average thermal energy. It's an average thermal energy of electron, so whose energy becomes equal to the Fermi energy, so that particular order of temperature which is known as Fermi temperature. So in order to raise the electron whose energy equal to the Fermi energy, for example, so if the electron which is exist in the Fermi level, so another electron which is exist in the bottom of the level, if you supply the energy, the bottom level electron whose energy rises till it rises which is equals to the Fermi energy, that order of temperature we need to be supplied. So which is equals to normally the Fermi energy or Fermi temperature which is bounded by the thermal relation. So that is why E is equals to K into Tf. K is Boltzmann constant, T will be the temperature we need to be supplied for a metal. The energy should be equal to the Fermi energy. So then Tf is equals to Ef by K. So then this order of temperature we need to be supplied. Next is, for example, the metal is having the 3 electron volts of Fermi energy. Its Fermi temperature is equals to 34,800 Kelvin. So it is a huge thermal energy. We can't possible to supply. So in order to vary the energy of Fermi energy of electrons, hence in ordinary temperature that Fermi energy did not vary. Hence even though we have defined the Fermi energy at 0 Kelvin, but the Fermi energy will not be varies at any temperature. If you raise the temperature, we can't possible to vary its Fermi energy till its melting point. Hence the Fermi energy is constant for a given metal. It won't varies with respect to the temperature. Hence the Fermi temperature is the average thermal energy acquired by the electron which is exist at the lower level and whose energy becomes equal to the Fermi energy. That particular order of temperature known as Fermi temperature. Next is the Fermi velocity. So I have already quoted only the electrons which are exist at the Fermi level, they are taking part of the conduction process. Hence whose velocity of the electron which is accountable whenever it is exist at the Fermi level. Hence the Fermi velocity is the velocity with which the conduction electron moves at Fermi level, where the electrons which is exist at the Fermi level, so the velocity of conduction electron at the Fermi level will nothing but the Fermi velocity. So which is equals to Fermi energy is equals to half m star Vf square. Here m star stands for effective mass of electron. I will explain it in the next slide what is effective mass, and Vf square is the Fermi velocity. Vf is Fermi velocity. So Vf is equals to 2Ef by m star over to the power of 1 by 2. This will be the expression for Fermi velocity of conduction electron. So the electrons are taking part of the conduction. Only the electrons which are exist at the Fermi level, they will going to participate in the conduction process, whose velocity is important because the electron which acts as a carrier for electric current. The velocity of electron will be accountable. the rest of the electron other than the electron which is exist at the Fermi level, which will be remain in the same atom, called as core electrons. Next is the effective mass of electron. The effective mass of electron is normally it's not a true mass of electron or rest mass of electron. So whenever the electron which is exist in the moving state whose mass is different from the true mass, so hence it is always phase whose mass is greater than that of the actual mass. Hence the resultant mass of electron when it is in a state of motion is called the effective mass. The effective mass of electron which is accountable. So normally whenever the electron whose mass is ME, we normally taken in all the examples it's a rest mass, but in the case of quantum electron theory we did not consider about the rest mass of electron. Instead of that we will consider the effective mass. Effective mass is, so whenever the electron moves by the influence of electric field whose mass is greater than that of true mass, the resultant mass of electron when it is exist in the state of motion, that particular mass is known as effective mass. Next is the mean free path. Mean free path of conduction electron, it is nothing but the average distance traveled by the conduction electron between the two successive collisions with the vibrating lattice point. This is known as mean free path of conduction electron, which is nothing but lambda f. Why we are supposed to be mentioning the lambda f instead of lambda? Because only the electron which are exist at the Fermi level, they will supposed to move inside the metal. Hence we will consider only the electrons which are exist at the Fermi level for the conduction process. Hence the lambda f is the mean free path of conduction electron at the Fermi level, whose equation will be equal to lambda f is equals to Vf into tau. Tau is the mean collision time of conduction electron at the Fermi level. So next is the expression for electrical conductivity in the case of quantum free electron theory. Using the Fermi-Dirac statistics, the Sommerfeld derived an expression for electrical conductivity of metals. The electrical conductivity of metals is depends upon the movement of electron which is only exists at the Fermi level. Hence we need to account its Fermi velocity, mean free path at the Fermi level before the electrical conductivity expression. Hence the electrical conductivity expression becomes sigma is equals to Ne square lambda f divided by m star Vf. In this case, in the previous discussion, the classical electron theory, instead of tau we have here lambda f by Vf. So in the tau is replaced by lambda f by Vf. So n is the concentration of electron, E is the charge of electron, lambda f is the mean free path of electron at the Fermi level, m star is the effective mass of electron, and Vf is the Fermi velocity of electrons. So this equation will explain all the failures of classical free electron theory, which is given by the Drude and Lorentz. Next is, what are the success? Success is, so to overcome the classical failures of classical free electron theory, this theory is framed. Hence we should account the same what are the failures of classical electron theory. Wherever it fails, there in that place the quantum free electron theory which successfully accounts the characteristics of metals. In the next slide, so the first one will be, before going to till the temperature dependence of electrical conductivity, I can show you a one video in which how the lattice bands are supposed to be vibrating with the mean position with the by raising the temperature of the metal. So now we can consider, see here there are the atoms which are going to be one dimensional array of atoms. So this is the positive ion core, and this is the neighboring positive ion core, all the atoms which are arranged in the regular fashion. So before the application of temperature, they will be exist at the mean position, and it seems to be like a state at rest. So but actually the lattice points will not be stay at rest at room temperature. They are supposed to be vibrating with a minimum amplitude, but we can't supposed to be notice at room temperature. So hence we should assume it as exist at the state of rest. Whenever if you start to rise the temperature, so here you can see that this bar will be stands for the increment of the temperature. So if the temperature is increased, the lattice points initially seems to be like a state at rest. So if the temperature is increasing, then it starts to oscillate or vibrates with the mean position. So these are all considered to be existence of area of atoms. It is similar to the existence of the position of atoms in the metals. So I will suppose to be increase the temperature. Then if the temperature is increased, then you can see that the temperature bar is supposed to be moving, means it is increasing. Then we can notice there is a vibration of positive ion core. They are supposed to be vibrating with the mean position. If it starts to vibrating with the mean position, it starts to block. Initially you can see that there is existence of more unoccupied space. Now it starts to cover. So the temperature is rising. Then the amplitude, you can see that have you noticed this? The amplitude is also going to be increasing. For higher temperature, the vibrating positive ion core is more. You can see that there is a vibrating ion core which increases the amplitude of oscillations. So because of the increment in the amplitude of oscillations, then the materials which starts to block the free movement of electron. Here you can see that in this particular here, this is the heat source, and this is the another hand, and this is the metal rod. There is a vibrating positive ion core in which the red dots are representing the vibrating positive ion core, the blue dots are representing the colliding electrons. If the temperature is increasing, so the amplitude of oscillation is also supposed to be increasing. Because of that, the electron undergoes more number of collision. Because of collision, it loses all its entire energy. So because of losing its energy, then it starts to block the path of electrons. So this is about the blocking because of rising the temperature of metals. So next is how we can supposed to be consider this factor for discussing the temperature dependence of conductivity. In the next slide you can see that, so this is the, you can see that these are the two figures which has the which has the positive ion core. This is red space representing the positive ion core, and the circle, white circle representing the area which is covered by the vibrating positive ion core. During the vibration, it undergoes covering the area. This is the area which is covered by the positive ion core. For lower temperature, it is the lower temperature. Similarly, positive ion core, if it is exist at the higher temperature, it can cover the more area. This is the covered region. So in the equation, Vf is independent on temperature. So independent of temperature, the rest of the terms in the existence, that is lambda f are constant for a given material. So we need to know about lambda f, which can be varies with respect to the temperature. Vf is constant, but the lambda f is going to be varies with respect to the temperature. The temperature can rise the vibration. So if the temperature is rises, the vibrating ion core is also rises. It leads to block the path of conduction electron. Hence the electron lambda f is going to be reduced because of rising the temperature. For lower value, so reduce the reduced to the lower value. Since R is the amplitude of lattice vibration, then the area of cross section is pi r square. Therefore, so you can see that this is the area of cross section of vibrating positive ion core, and this is the area of cross section of positive ion core. This is for the lower temperature, this is for the higher temperature. You can see that the area which is covered at the lower temperature is low than compared to the area which is covered at the higher temperature. You can see that this is the positive ion core. I will suppose to be show here, this is going to be vibrating with a mean position. See, this is the vibrating positive ion core for the lower temperature. For lower temperature, if the same metals whose temperature is raised, then it starts to vibrate and it starts to cover with more area. If it starts to cover more area, hence it starts to block the path of conduction electron. So because of blocking of the path of conduction electron, lambda f, that means mean free path of conduction electron, starts to rise whenever the temperature is increased. So I will consider this will be for giving the solution for the success of quantum free electron theory. So let us consider the same expression, that is lambda f mean free path of conduction electron is inversely proportional to the area which is covered by the vibrating positive ion core, that is pi r square. So lambda f is inversely proportional to the pi r square, where r is the amplitude of lattice vibration, or you can say it is a radius of amplitude of radius of the circle, which is normally equal to the amplitude of lattice vibration. The thermal energy is the square of the amplitude, hence r square is proportional to the temperature. From 2 and 3, we can suppose to be directly write lambda f is inversely proportional to the temperature of the metal. So lambda f is always going to reduce whenever the temperature is increased. From 1 and 4, 1 is the expression for electrical conductivity of metals, that is in the case of quantum free electron theory, sigma is equals to n e square Vf by m star lambda f. We already seen this is in the case of sigma is equals to n e square lambda f by m star Vf. Because of that, sigma is inversely proportional to the temperature. From equation of electrical conductivity of metals and the lambda f is inversely proportional to the temperature, and sigma is inversely proportional to the lambda, directly proportional to the lambda f. So because of that, sigma is inversely proportional to the temperature. So our sigma is inversely proportional to the resistivity of metal. This is the right expression. Experimentally also, sigma is inversely proportional to the temperature. This is the right expression of temperature dependence of electrical conductivity of metals. Hence, the quantum free electron theory successfully explains the temperature dependence of electrical conductivity of metals. Next is another failure, that is see in the case of classical electron theory. Classical free electron theory will not supposed to be explained satisfactorily why the conductivity is different from why the conductivity of copper is different from aluminum, even though it has more number of electrons. So here sigma is equals to n square lambda by m star Vf. The conductivity of copper is higher than that of aluminum. So the conductivity of copper is more than that of aluminum. Aluminum is having the more number of concentration of electrons than compared to copper. However, it has more conductivity in the case of copper. However, the concentration of electron in the aluminum is 2.13 times more than that of copper. So copper is more conducting than compared to aluminum, even though it has less concentration of electrons. However, the lambda F by Vf in the case of copper is 3.73 times greater than that of aluminum. So even it is having the lesser concentration of electrons, but lambda F by Vf is here. Lambda F, copper is having the low value of n. However, but lambda F by Vf is more than aluminum in the case of copper. And also the effective mass of aluminum, the effective mass of electron in the aluminum, that is m star, is 1.08 times higher than that of copper. So in the case of aluminum, the electron effective mass is more, hence the data suggests that even though the concentration of electron is large in the case of aluminum, has less value of lambda F by Vf and more value of m star. Due to this, low conductivity is observed in the case of aluminum compared to the copper. So this is the right explanation which is given by the Sommerfeld. So through his equation called as sigma is equals to n square lambda F by m star Vf. This is all. With this we completed the electrical conductivity of metals. So in the next video I am going to discuss about the semiconducting materials. Thank you very much.